Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 36. We're lecture 17, and in this video we're going to discuss confidence intervals for proportions. Okay, so we've done the confidence intervals for some means, difference of means. Now we're going to look at something very different. Suppose we wish to estimate the proportion P, so this is our population parameter, P, of objects in a population, that's the abbreviation for population, that have some attribute of interest. So it's some category. Now, before we continue, if you remember from the binomial distribution, the binomial distribution requires us to have two categories. But if something has more than two categories, we can always reduce it to some characteristic of interest versus everything else. For instance, we may have a category called mobility problems. And the categories may be none, no problem with mobility, minor, significant, or substantial, and extreme problem with mobility. In other words, maybe they can't move at all. So this has more than two categories. What we can do and what we may do is we may say that we're interested in those that have any problem with mobility versus those that don't have any, not any. Okay? And so even if you have more than two characteristics, we can still use this method. We just have to choose one of those proportions that we're interested, or one of those proportions we're interested in estimating. Okay? So we have to choose the proportion for one category that we want to investigate. All right. So here's an example. We may wish to estimate the proportion P of voters in a certain district that favor health care reform. 2, the proportion P of a large population of manufactured items that have a certain defect. So again, the items may have several different defects, but we're going to choose one of them and estimate that. So in order to estimate the parameter P, we need to first select a random sample of n objects, and we need to then count the number y, we're going to call it y, of objects in the sample that have the attribute of interest. Now there's two ways that we can sample. The first is we sample with replacement. So we randomly select from a population, then we put the individual or the member of the population back in the population, and then we randomly select again, and we keep doing that until we have n. That is perfectly independent sampling, right? Sampling with replacement means that each observation is completely independent. And so y has exactly a binomial distribution with n objects, the sample size of n, and P is the proportion of the population that has the attribute of interest, which we don't know. And so it's exactly a binomial distribution. Or what we normally do is sample without replacement, but from a large population. And then we can say that y has approximately a binomial distribution. But what are the rules for this? So the rule for this is that little n, our sample size, has to be less than 5% of the population sample size. This is called the 5% rule. Now, our book, I think, says n is much, much smaller than 0.1 n. Okay, but how much smaller is that? That's not very specific. So one of the rules that I like to use is that the sample size is less than 5% of the population size. Okay, so that is a rule you need to know. So let's talk about how we calculate the sample proportion of the attribute of interest, and sometimes we call them success versus failure, and that becomes problematic when we are interested in studying death, the causes of death. Well, that means that since you're interested in studying the causes of death, you're calling death a success, but none of us want to do that, I don't think. So this term success has to be used intelligently. But if somebody says success, just remember it doesn't necessarily mean what we consider to be a success, just the attribute of interest. So we do that by p hat is equal to y, which is the number of items in the sample that have the attribute of interest, divided by the total number of items in the sample. So makes perfect sense. It's a proportion. We could multiply it by 100 and get percentage. So those are equivalent ways of expressing something. So if I have p equals 0.15, that is identical to 15% of that sample, or p hat, I should say. Okay. Now, if we take the expected value of y, we've done this. We proved this last semester. The expected value of y is n times p, and of course that's mu. Okay, so mu is equal to e of y, which is n times p. And we showed that the variance of y is n times p times q. So sigma squared equals npq. And q is equal to 1 minus p. Okay. So let's find out what the expected value of p hat is. Why are we doing this? We want to find z, which is equal to the standardized form of p hat, let's say sub p hat. And so that will be p hat minus e of p hat divided by the standard deviation, or the square root of the variance of p hat. So we need to find e of p hat, and we need to find the variance of p hat. So the expected value of p hat, we substitute in the equation for p hat. That's y over n. Now, y is the random variable. N is the sample size. In this case, we're going to assume that that's a set quantity. I can rewrite y divided by n as 1 over n times y. And if this is a constant, then it simply comes out. We have that property that says the expected value of a constant times a random variable is equal to the constant times the expected value of the random variable. So 1 over n e of y. Well, we know what that is. E of y is up here. It's n times p. So 1 over n times p. And so this n and that n, they cancel out, and this is equal to p. So that means that e of p hat is equal to p. It's an unbiased, p hat is an unbiased estimator of p. So that's nice. And so the MSE, the mean square error of p hat, is equal to the bias of p hat, quantity squared, plus the variance of p hat. But we just determined that the bias here is 0, so it's just equal to the variance of p hat. So what is the variance of p hat? We need that in our formula. So we take p hat and we plug in the value for p hat, the formula, so y over n. And again, I can write that as 1 over n times y. Same thing. And n is a constant. Now, remember that we have this property for variance that's different than expectation. Variance of c times x is equal to c squared times the variance of x. So we end up with 1 over n squared, because 1 over n squared, 1 times 1 is 1, over n squared, right? So we're just going to go ahead and write it as 1 over n squared. Oops, clicked the wrong thing. And then we have times the variance of y, which was npq. So I have 1 over n squared times n times p times q. One of these n's cancels, and I get pq over n. And that is the value of the variance of p hat. So now we're ready to do our standardized form. And so of z of p hat, the standardized form of p hat. And so we plug in for the expected value of p hat, that was just p. And the variance of p hat, that was p times q over n. And it's inside the square root. So this is our standardized form of p hat. We've standardized it. We've subtracted the mean. We've divided by the standard deviation. Now, this is, so some of you had trouble understanding what the requirement was on the last test for using the binomial approximation to the normal, or the normal approximation to the binomial distribution. Almost said it backwards, or did say it backwards. It's n times p is greater than or equal to 5. This is what I'm looking for. Put down anything else and I will count off. Okay? So in this class, we're looking at n times p greater than or equal to 5, and has to both be true, n times q greater than or equal to 5. So the minimum value of n is 10, because you have to have 5 in each category. That's what this is saying. N times the proportion, that's 5. 5 individuals, at least 5 individuals in both categories. That means that n has to be a minimum of 10. If it's less than that, guess what? This doesn't work. It's not a good estimate. So when this is true, we use the central limit theorem to say that z of p hat, if you want to say of p hat, z, which is equal to the quantity we just calculated, has approximately, this means approximately, a standard normal distribution. Not exactly, but approximately a standard normal distribution. Okay? Therefore, we're going to derive the confidence interval the same way we did before. So since we know that z is approximately standard distributed as an approximate standard normal distribution, we can say, using the standard normal distribution, we can say the probability that capital Z, our standardized form, is between negative z naught, some number negative z naught, and positive z naught, that we set that probability equal to 1 minus alpha, which is we call it a coverage probability. I explained that before, coverage probability, which in this case is also the confidence level. Okay. And so I'm going to solve for p. I need to isolate p. The first thing I'm going to do is multiply by the denominator. So that's getting too messy. I want to isolate p, and so my first step is I'm going to multiply all 3 parts of this inequality by this denominator. It will cancel out in the middle portion, and I will be left with the probability that negative z naught times the square root of p times q over n is less than p hat minus p is less than z naught square root p times q over n is still equal to the same value, 1 minus alpha. Now I'm going to multiply by negative 1 for all 3 portions. I end up with z naught square root pq. Why? Because I want to get the p to be positive. It's negative right now, and I don't want it negative. So if I multiply everything by a negative, then p will be a positive. And so that is square root of n And now if I multiply by a negative, I have to reverse the signs. So greater than p minus p hat. So I could write this negative p hat plus p, but I really want p by itself, so I'm just going to put it first. This works too. It's more efficient. Is, wrong way, is greater than or equal to negative z naught square root of pq divided by n. And now I'm going to add p hat to all three parts of the inequality. So I have p hat plus z naught square root pq over n is greater than or equal to p, is greater than or equal to p hat minus z naught square root of pq over n. And now I'm just going to rearrange this in the right order. I'm going to put the smallest value, the minus z naught, to the left and the largest value to the right. And so that means I need to change the sign. So I have p hat minus z naught square root of pq over n is less than or equal to p is less than or equal to p hat plus z naught square root pq over n. And so this is my 1 minus alpha times 100 times 100% confidence interval. So I could write that as p hat plus or minus z naught times pq over n, where the probability that z is greater than z naught is equal to alpha over 2. Why? Well, what we did was we said, okay, standard normal, it's symmetric, and we have z naught, and then we have negative z naught, and in between is 1 minus alpha. So the remainder is alpha, and it's in the center. That makes sense that we put it in the middle. And so what's left over is alpha over 2 over here and alpha over 2 over here. Now, if I add all three of these circled quantities, it adds up to 1, which is the area under the curve, or the total probability of the probability distribution. So z naught is a critical value. It could be written, and it is, as z sub alpha over 2 in many formulas. Our book just calls it z naught, okay? Which may become confusing when we start talking about hypothesis testing, but we'll worry when we get there in chapter 8. So we can find z naught by this equation here. So you see z naught is here, and the probability above, or that z is greater than z naught, is alpha over 2. Let's do an example. So let's say that n is equal to 36. It's always nice in an example to have a number that's you can take the square root of. And then we're going to say that y is equal to 8, and we want a 90% confidence interval for p. The first thing that we should probably do is calculate p hat. And so p hat is y over n. Y is the number of items that has the attribute of interest. So you could be given a data set. In fact, some of the homework problems may have a data set and you have to count what y is. Here I've given us y. So p hat is going to be 8 over 36, which if you divide both by 4, you get 2/9, and that is 0.222, and it just keeps going. And so we're going to, for the sake of the example, we're going to round this to 0.222. So we're going to leave it at 4 decimal places. Normally, you would plug in 8 over 36. Actually, we will. We'll use exact values. It's not difficult in this case. So I will reduce it to 2/9 just because that's easier to manipulate. All right. So the next thing we should probably do is we want to find z naught. So C, the confidence level, is 0.90. and alpha equals 1 minus c, so 1 minus 0.90 equals 0.10. And thus alpha over 2 equals 0.05. So we have this relationship that we have z naught here, and over here we have 0.05, and that means that here we have 0.95. And we could, since we want the probability above, or this is the probability that z is greater than z naught, we can use table 5b in our book. So let's find the tables. Let's go to the normal distribution. And we can do that. But I also wanted to point out that we have z sub alpha, or z sub alpha over 2, if this is alpha. They give this for alpha equals 0.1. That's what we have. And so this is 1.645. Okay. So, and notice these numbers are the same. And these numbers. And that's because we're dividing by 2 and dividing by 2. Notice that that doesn't work when we go from 0.025 to here. But when we go from 0.02 to 0.01, we're dividing by 2. And when we go from 0.01 to 0.005, we're dividing by 2. So that works again. Okay. All right. And you'll see going from 0.2 to 0.4 that it works. All right. So our number that we want is 1.645. You could also come over here and try to find 0.05. You're not going to find it exactly. It's going to be between these, exactly between, so you can't use either one of these. Neither one is closer, so you have to go right in the middle, which is halfway in between. So make sure that if you're doing a confidence interval or a hypothesis test, if there's a value, if the value of alpha is up here, use it. Because if you use 1.64, that's not right. If you use 1.65, that's not right. So the value is 1.645. Okay. So z naught is 1.645. Now, we need to calculate p hat plus or minus z naught times the square root of pq over n. P hat, we've said, is 8 over 36. And then plus or minus 1.645. And then it gets a little messy here because, so we have 8 over 36 times 1 minus that. So 36 minus 8 is going to be 28 over 36. And then divided by n, which is 36. Now, since we're all mathematicians, I hope this is not too difficult for you to see. When you're using fractions, it's a lot easier to write this as whatever the fraction denominator is, cubed, and then 8 times 28. That's a lot easier for me to put in my calculator. So I have 8 over 36 plus or minus. I'm going to calculate this right now. So I have second square root. Ooh, sorry about that. Let's come back down. Okay. Hit a invisible button on the iPad that made it go to the start. Okay. So I have second square root 8 times 28 divided by 36 cubed, close the square root, and then times 1.645. And that is 1.1398197004. I'm going to round this to 3 decimal places. I want my answer to 3 decimal places, let's say. So we can't round before then, but now we can round to 3 decimal places. Oh my gosh, there's so many hidden buttons here on this thing. So 1, 2, 3, 4. So this is going to be 0.114. And to 3 decimal places is going to be 0.222. So I'm going to get my lower number is 0.222 minus 0.114, and my upper number is 0.222 plus 0.114. And this is going to be 0.222 minus 0.114, 0.108. And this is going to be 336. And anytime, I should say every time you calculate a confidence interval in this class, you need to interpret it. That is what statistics is about. It's not about finding this number. That's just math. Statistics is explaining it. Okay? So we are, not can be. It's not that we can be, we are. So please don't say anything else. We are 90% confident that the interval, so we have a blank there that you need to fill in, that the interval, and this is a blank, 0.108 to 0.336. So that's a little messy. There we go. Contains the true proportion of whatever this is. And we don't know. We weren't given in this case. So we would just say the true proportion of the population with this certain attribute. Yeah. Okay. Using a random sample of n equals 36, whatever it is, objects, items, but units if you have it, okay? All right. And so that is how we calculate a confidence interval. All right, that's it for this section. I hope this has been easy enough for you. If you have questions, please come to virtual office hours. If you need help before office hours, then by all means email me, but make sure you email me a copy of the question so I know what question you're working on. I don't have them memorized. And a copy of your work so far so I can see how you are approaching it, and then I will get back to you as soon as it's possible, and that will allow me to help you the best way. Please take care of yourself because we want to see you here next time.